when the universe was dark, silent, and empty. A time before the first stars were born, before the first galaxies were formed, before the first light was emitted. This is the cosmic dawn, the earliest epoch of the universe, about 100 million years after the Big Bang. But what happened during this mysterious period? How did the first stars come into existence? And how did they shape the evolution of the cosmos? These are some of the questions that astronomers have been trying to answer for decades, but they have faced a major challenge. The first stars are extremely hard to find. Their light is very faint and redshifted by the expansion of the universe, making them invisible to most telescopes. In this video, we will explore how James Webb Space Telescope was able to do that, what it can learn from the first stars, and what are the challenges and limitations of its search. We will also discuss why finding the first stars is important and what it means for our understanding of the early universe and the origin of the cosmic structures we see today. So stay tuned and get ready to witness the cosmic dawn with Webb. The first stars are believed to have formed from the primordial gas that filled the universe after the Big Bang. This gas was mostly hydrogen and helium, with traces of lithium and other light elements. The gas was initially cold and dense, but it gradually heated up and thinned out as the universe expanded. Eventually, some regions of the gas became denser and collapsed under their own gravity, forming the first stars. These stars were very different from the stars we see today. They were much more massive, ranging from tens to hundreds of times the mass of the sun. They were also much brighter, emitting thousands of times more light than the sun. And they were much shorter-lived, lasting only a few million years before exploding as supernovae or collapsing into black holes. These stars had a profound impact on the later evolution of the universe. They produced the first elements, such as carbon, oxygen, and iron, that enriched the intergalactic medium and enabled the formation of planets and life. They also ionized the surrounding gas, creating bubbles of hot plasma that eventually merged and reionized the entire universe, making it transparent to light. And they seeded the formation of the first galaxies, which grew and merged over time to form the large-scale structures we observe today. But how can we find these stars and study them? This is where Webb comes in, which is designed to observe the infrared light from the first stars that is beyond the reach of other telescopes. First stars are so far away that their light has been redshifted from the visible and ultraviolet range to the infrared range. So Webb has to use different techniques and methods to find the signatures of the first stars in the spectra of galaxies, such as looking for the presence of certain elements, the intensity and shape of the emission lines, and the fluctuations in the brightness. It also can measure the amount of helium in the spectra of galaxies by looking at the emission lines of helium, which are the peaks of light at specific wavelengths that correspond to the energy levels of helium atoms. Finding the first stars in the universe is not only a technical challenge, but also a scientific opportunity. By observing and studying the first stars, Webb can learn a lot of information that can help us understand the early history and evolution of the universe, and test and refine the theoretical models and simulations of the first stars and their formation processes. Some of the information that James Webb can obtain from the first stars are their properties, such as their mass, luminosity, temperature, and lifetime. These properties can tell us how the first stars were different from the later stars, and how they affected the surrounding environment. For example, the mass of the first stars can determine how much energy and radiation they emitted, how long they lived, and how they ended their lives. The luminosity of the first stars can determine how bright and visible they were, and how they ionized and heated the intergalactic gas. The temperature of the first stars can determine what kind of elements they synthesized and how they enriched the intergalactic medium. And the lifetime of the first stars can determine how long they influenced the early universe and when they gave rise to the first supernovae and black holes. Moreover, their numbers, distribution, and diversity. These factors can tell us how common and widespread the first stars were and how they varied across different regions and times in the universe. For example, the numbers of the first stars can determine how many of them were formed, and how they contributed to the reionization and chemical enrichment of the universe. The distribution of the first stars can determine where and when they were formed, and how they clustered and correlated with the density and temperature of the primordial gas. And the diversity of the first stars can determine how they differed in their properties and behaviors, and how they depended on the initial conditions and feedback effects of the primordial gas. Also, their connection to the subsequent generations of stars and galaxies. This link can tell us how the first stars influenced and shaped the later evolution and structure of the universe, and how they relate to the observable objects we see today. For example, the connection of the first stars to the later stars can determine how the first stars transferred their energy, radiation, and elements to the later stars, and how they affected their formation and evolution. The connection of the first stars to the later galaxies can determine how the first stars triggered and facilitated the formation and growth of the first galaxies, and how they determined their properties and morphology. And the connection of the first stars to the observable objects can determine how the first stars can be traced and identified by the light and signals they emitted or left behind, and how they can be compared and contrasted with the objects we see today. Webb can also test and refine the theoretical models and simulations of the first stars and their formation processes, and see how well they match and explain the observations. For instance, it can test the effects of dark matter, cooling, feedback, and metallicity on the formation of the first stars, and see how they agree or disagree with the predictions of the models and simulations. It can reveal new and unexpected phenomena and raise new questions about the first stars and their role in the universe, and challenge and inspire the development of new models and simulations. We can use it to compare and contrast the information from the first stars with the information from the later stars and galaxies, and see how they are similar or different, and how they are connected or separated. Also, we can synthesize and integrate the information from the first stars with the information from other sources and wavelengths, and see how they complement or contradict each other, and how they form a complete and coherent picture of the early universe. Webb is a remarkable telescope that has the potential to find the first stars in the universe, but it is not a perfect or easy task. It may face many challenges and limitations in its quest for the first stars, such as the contamination from other sources of infrared light that are coming from the first stars is not the only infrared light in the universe. There are many other sources of infrared light that can interfere with or obscure the detection of the first stars, such as the dust and gas in the interstellar and intergalactic medium, the stars and galaxies in the foreground and background, and the zodiacal light from the solar system. These sources of infrared light can create noise and confusion in the observations of it, and make it harder to isolate and identify the signal of the first stars. Webb will have to use various techniques and methods to reduce and remove the contamination from other sources of infrared light, such as filtering, masking, subtracting, and modeling. The calibration and interpretation of the data that Webb will collect from the first stars is not straightforward or simple. It will be affected by many factors and uncertainties, such as the instrument performance and sensitivity, the observation time and strategy, the data processing and analysis, and the theoretical assumptions and models. These factors and uncertainties can introduce errors and biases in the data and make it difficult to calibrate and interpret the data. It will have to use various techniques and methods to improve and validate the data, such as cross-checking, correcting, testing, and comparing. These are some of the examples of the challenges and limitations that it may have in its search for the first stars, and there are many more that can be encountered and overcome. Webb may not be able to find the first stars with certainty or conclusiveness, and it may require more data and analysis to confirm and refine the results. It may also need the help and support of other telescopes and wavelengths to complement and enhance its search for the first stars, such as the use of radio, optical, and X-ray telescopes, the combination of different types of data, such as images, spectra, and signals, and the development of new technologies and methods, such as machine learning, artificial intelligence, and quantum computing. This will open new avenues and opportunities for the search and study of the first stars, such as the discovery of new and unexpected phenomena, the generation of new and intriguing questions, and the inspiration of new and innovative ideas. We have reached the end of this video. I hope you enjoyed this video and learned something new and interesting. If you did, please give it a thumbs up and share it with your friends and family. And if you want to learn more about this topic and other topics related to astronomy, astrophysics, and cosmology, then please subscribe and hit the bell icon so that you don't miss any of our upcoming videos. Thank you for watching, and see you next time.